if I turn the wheel of this to the clockwise, it spins clockwise. And if I turn it counterclockwise, it goes counterclockwise. So a couple of weeks ago, I made this video about the Rotary Encoder and how it works, and basically how it's this little wheel that has multiple contacts, an A contact and a B contact and a common contact that's connected to ground. And what happens as you rotate the wheel in either direction, the contacts are made at different times, and you could tell based on which one goes on first and goes off first whether you're rotating it clockwise and counterclockwise. So I made this little circuit here that connects to a D flip-flop, and basically the output of that, the Q of the D flip-flop, I used a CD4013 in this case, tells you whether it's going clockwise or counterclockwise. So now I used that to control a motor in the previous video, but that's not the ultimate purpose of that. I decided to make a new project, and I connected that rotary encoder circuit, which is miniaturized here, same one as there. And the way the circuit works is that the A contact is connected to the C contact with a debouncing capacitor here, a 10 nanofarad capacitor, and same thing with the B contact. I have here two LED drivers which indicate when the A contact is being made and the B contact is being made through these little NPN transistors, and the outputs of these are sent to the D flip-flop. So here's the circuit with the D flip-flop, and I have here a set of CD4029 binary 4-bit up-down counters. And so I want to create a count up to 17 bits. So this is a 17-bit counter. And so the way I did this was, you can control on the fly whether the output is up or down, whether it counts up or down, and just by connecting that D flip-flop in here to the up-down pins of all of these, which is wired in parallel, there's a separate clocking mechanism. My clock here, you can use any oscillator, but I'm using a CD40-106, and basically I have a 16 kilohertz counter, and these are cascaded so that the carry out of each is going to the carry in of the next one. The first one, the least significant bit one, I have temporarily connected to the A output of the rotary encoder, so I can stop the clock periodically and just pulse it because it counts so fast. But this can be free running and just basically connected to ground without this here. And so I have 4, 8, 12, 16, and then the first output of this is the most significant bit. That's the 17th bit connected. And so that is basically an interface for our rotary encoder to control a 17-bit counter, which on the fly we can change the count to up count or down count, and stop it and pause it along the way to see where it needs to stop it where we think it needs to be. So let's implement this and let's build it. So here it is, all built up. I'm clocking it here at 21 hertz, slower clock, just so I could see all the bits lighting up. And you can see the counter is counting up right now. And it's going to count up slowly because it's going to take a while to get to 17 bits. But here are all the 5 CD4029 counters. And when I change direction, on the rotary encoder, you see the light in the upper right corner change direction, and now it starts counting down. So it's working just fine. So I have here my rotary encoder circuit from a computer mouse. And so this is basically the A, B, and the C. The blue is the A, the green is the B. and the yellow is the C, which is the ground. And I have a D-bounce with these capacitors here, and as you can see on the right side, I have a CD4013B D flip-flop. It's a dual flip-flop, but I'm using one of them. And the outputs from pin 1 and 2 are the outputs of the direction that it's going in. So if I turn this clockwise, the Q, which is the light that's currently on, goes on, and no matter how much I turn them clockwise, it stays in that direction. Now if I turn it counterclockwise, it's going to go the opposite direction, which is the Q bar, the pin 2 output. And I have the outputs on the left side. I have a CD40106 as a 16 kilohertz clock, basically a square wave. And what that's doing is that's clocking in providing the clock signal for these 5 CD4029 up-down binary 4-bit counters. And these are hooked up to an output, and currently I have the clock paused. But as I turn it clockwise, it counts up. And when I turn it counterclockwise, it counts down. And I have 17 bits of information. And you can see the clock is going so fast that you can't see the first 10 bits of it. But count up and count down. So I have the clock stopping based on the output of the A, which is this light. So if I have the A go on, the clock stops. And if I have the A going off, the clock restarts. So in this way I could rapidly control where the clock will stop on which bits. That way I don't have to cycle too much through these clock bits. So in any case, at a frequency of about 16 kilohertz here, the frequency can be adjusted with this potentiometer right here, but at a frequency of 16 kilohertz, it basically takes about 8 seconds to count all the way up to the 17th bit position, which is equivalent to about 128,000. So next step is, what are we going to do with this? Well, we shall see. Stay tuned. So I'm going to leave you with the schematic of the Rotary Encoder circuit and the interface for the CD4029 binary counters.